Hey, hey, willkommen. Jag heter Martin. My name is Martin, and welcome to the Design of Embedded and Intelligent Systems course. Today, we're talking about computer vision, and the goal is to hear about some common approaches that will help you to design such systems. Computer vision is a powerful recognition modality with growing opportunities, but we can only talk about a little bit today because there's so many topics to cover. But we can start with color. There's many interesting concepts regarding color, and it's useful because you can use color-based techniques in conjunction with intensity-based techniques and achieve more accurate results. One thing that you often want to do with color is you want to find some type of colored marker on a robot. And one way you can do this is to transform your image to HSV color space and then threshold on hue value. What is hue? Hue is what we usually talk about when we talk about colors. That's if something is red or blue or green. Saturation is how gray something is, and value is how dark or light it is. If you have a bit of more complicated problem, like you want to detect skin in an image, then maybe using hue to color pick is not so easy. Instead, you can calculate a histogram from some type of template image, like you can take a picture of your hand, and then in some type of target image, like a picture of your face, you can look for each pixel and set the output as the value of the histogram bin that you calculated with the template image of your hand. So I'm doing this at the bottom right in this slide, and it looks a little bit dirty probably, but if you use some of the techniques we talk about later, like contours, you can extract your face quite nicely with this. Color tracking, you don't want to detect colors in every image because that is slow and also unstable. So you can use some techniques like mean shift, for example. Here you've got a circle, and within that you've got some points of interest. This might be like pixels that you've identified as skin. What you do is you iteratively calculate the centroid within that circle with based on those points of interest. And you'll find here that your circle will go up and to the right until it has the most points of interest that it can get. So when something is moving across your video, you can track it. Cam shift is very similar. You also compute mean shift at the beginning, but then you also look at a little bit of a wider area, and then you fit a rotated ellipse to that to really deal with things like when the thing you're tracking becomes bigger or smaller because it's getting closer or further away, or if it's becoming rotated. Smoothing is a very common operation which can help you to reduce noise that might not be removable in some nicer other way. So what you can do is you can just look at the neighborhood of a pixel and you can take the average, for example. When Gaussian noise is applied, a Gaussian is also very useful. So here is an example of a one-dimensional Gaussian. And on the right, you can see an example of smoothing on this normal video that's at the top, where I've used a bilateral filter, which is nice to retain edges while still doing smoothing. Morphology is another way to reduce noise. So if we look at the center picture here, if we think that this thing is noise and we want to get rid of it, we can erode, which makes this thinner, and then dilate to make it the same size again, but this will be gone. Otherwise, if we think that there's a little hole here that we want to fill, we can do the reverse. We can dilate first and then get rid of that black space and then erode to restore it to the same size. So on the right, there's on the top, this is an example of erosion. You can see that my eyes and nostrils are quite dark and I look thin. At the bottom, this is an example of dilation. I look quite fat and it's hard to even see my eyes. Thresholding is another way to reduce noise or to even segment out some object that is of interest to you. And what you do is you set pixels to black or white by comparing their intensity to some threshold. You can use some type of binary threshold, or you can use an automatic method like Otsu's method that will find a nice threshold here between two distributions based on the assumption that you've got some type of distribution of noise and then a distribution that you're interested in. On the right, here's an example again of thresholding. You can see there's some white areas on my face, and then the darker areas, there's more red or yellow that comes out. Edges, this is really an important topic in computer vision, and it's a way to reduce the information in some image while keeping the most meaningful parts. Very common pre-step to various approaches, other approaches. How do you do it? Well, you calculate the gradient and you threshold that, and you remove thin edges, stuff that might just be noise. Sobel filter is a nice, simple way to detect edges. You pass two matrices over your image, one in the X direction that will find vertical lines, one in the Y direction that will find horizontal lines, and then you take the Euclidean to find the magnitude of the gradient. You can also get the angle with the inverse tangent. These edges that you find, there can be some spurious edges there. It can look a little bit fat. So people often use something called canny edge detection, which first uses smoothing, then it uses a Sobel filter, and then it also checks if it uses three categories: if there's no edge, or if there's a weak edge or a strong edge. And if there's a weak edge, it also checks the hysteresis. It checks, is this weak edge connected to another pixel, which is labeled as a strong edge? Then we can keep it. So this will give you thinner edges. Laplacian is another technique. It's fast, but it finds the zero crossings of the second derivative. So it's a bit weak to noise, and you should smooth before using it usually. Huff transform is another cool operation that can be used to find shapes like lines and circles in your image. And you might say, but wait, we just did that with edge detection. Well, edge detection is usually quite fragmented, and often you want to know really, are there lines? Where are they? So you can do this by looking for every pixel in your image of your video. If there's a line, if it seems like there's a line passing through that pixel, and that's parameterized to avoid cases where you might have a vertical slope, which would be infinite if you're using, y equals mx plus b, that type of thing. And basically, you then look throughout your image and you increment these accumulator bins. So if you have a bin where there's many times accumulated, you use a threshold on that, and you can see there's probably a line there. So this is what I'm showing at the bottom right. It's picking out the window beside me quite nicely. You also see some noise, so you have to look at the parameters. I want to compare that also with something called random sample consensus, RANSAC. And this is a technique to find one line within an image. And this is a little bit different. The idea is that you'll have lots of outliers maybe in some data. And so you can't just use something like least squares to find a nice line to pass through your data. Instead, what you do is you pick a small subset of your data points, and then you fit a line to that. And then you check what other data points are close to this line. Then that becomes your new consensus set, it's called. And then you again fit a line based on it. You do that iteratively. Okay, so we're about halfway through, so if you want to take a break, please pause the video and then go on when you feel relaxed, when you've got your coffee again. So next we look at background subtraction. This is another way to find objects within some type of video or image. And specifically, it's finding the foreground, segmenting that out. And the easiest way to do this is shown on the left here. If you have some type of image and you have a background image then you can, for example, capture these people here who are moving through the corridor by subtracting these images. On the right, I'm showing something a little bit more complicated. This is using a mixture of Gaussians to model a background that's a little bit dynamic, where you have maybe illumination changes or whatever. So if I don't move, then you can see that I fade into black, and it's only the parts of me that I'm really actively moving that are white. Contours are also really, really useful, and it's basically the outline of some blob or something that you're looking for in an image. Why are you interested? You often want to process the region of an image just for some object or show it. Here on the left, you can see an example of a contour that you've created around some points that might be in a mask image. Convex hull is similar, except you don't have those concavities that you saw. Everything's convex. And then bounding box is just a minimal box that will enclose this data. Why do we care about this type of thing? Well, you can do lots of really useful things with it. For example, you can find the distance to some type of marker using triangle similarity. So there's a very nice example on the internet of how to do that. But basically, you just sort of learn this relationship between lengths within your image and the actual lengths to be able to find the distance to some marker that you identify with the contours. And here on the right, I'm showing an example of finding contours based on canny edge detection. You can see there's quite a bit of noise, it looks like, but you're grabbing like my head and my hair over there. Template matching. This is another really simple, useful technique. If you know that you're looking for something specific, then you can just take that template of that thing that you're looking for and pass it over the image, and then use some type of threshold on the match to say when you found it. So here, there's a video playing that's showing an example of a robot a student built that will patrol around in an environment. And when it sees itself in some type of reflective image, it checks to see if it's okay. And here it's found that it's got a problem, so it tries to fix that. Other segmentation, there's many, many ways to do image segmentation. So about 10 years or so ago, graph cuts were really popular. Maybe they still are. This is sort of where you model the pixels in an image as nodes in a graph, and then you compute where the weaker edges are, and you can slice through that to segment the image. Clustering, like with k-means, like we talked about, is another way to do segmentation. Watershed is well known. Snakes, active contours, so you can gradually converge to a more complicated shape from using a simple shaper around whatever you're looking for. Features is another very fundamental and important topic in computer vision. It's another way to have a reduced meaningful representation based on finding important defining points within an image. And you can use that then for detecting images, for matching different things in images. I'll talk about one example of a type of feature called SIFT. How do you calculate SIFT? Well, you find a difference of Gaussians you use a difference of Gaussians to find edges at different scales. Using gradually stronger Gaussians, you check the neighborhood within the scale space. And you remove low contrast points, points on edges, and you form neighborhood descriptors using codebook bins. So this is shown a little bit here on the left. You've got a bunch of gradients, and then you will represent that as a descriptor. And then when you want to match things in different images, you can use nearest neighbor to match keys, and then Huff transform to cluster poses, because you probably have lots of different features, different objects. and then you can use least squares to find the transformation there. On the right, I've got an example of using a different kind of feature called orb. I'm using that because SIFT is patented, so it's not so easy to use, and it's a little bit interesting. You can see that it seems to think that my ears, my glasses, my nose are very defining for me, and it's also catching a glass I've got on the windowsill for some reason. Viola-Jones is another amazing algorithm that came out maybe 15 years or so ago as a way to detect arbitrary objects in a very nice way. This made face detection, for example, online. Problems is that you often need many training samples if you don't have some readily available data set for what you're looking for. And it's not that fast. There have been faster algorithms now to do different things like that. But I want to talk about 4 concepts in Viola-Jones that I think are important. The first one is the integral image. So if we want to compute the sum of the intensities of the pixels in some region, like region D, how can we do this fast? Well, one way is to prepare some image called the integral image, where every pixel in here, the value of that pixel will be the values of the intensities of the pixels above it and to the left of it. So then if we want to find the intensities in region D very fast, well, it's just the intensities, the intensity of the integral image at D plus the value at A minus B minus C. And that allowed for a massive speed up. Haar-like features are a major important part of this algorithm as well. And this is basically comparing box-like regions across an image. So you can see that you can detect that in a face, this part of my face, the eyes, the eyebrows will be darker than the cheek. And then the nose is usually lighter than the area around it where there's shadows. Viola-Jones also uses boosting then. It uses those features as weak learners. And that means that you will use some feature, like for example, to find the cheeks and the eyes. And then you reweight the samples, you reweight the data that's misclassified using that feature to make it more important. You find another weak learner that will be able to deal with that well. And then by adding all of these weak learners together, allowing them to vote, you will get a good classification. Now, they took it even further and they organized several boosting learners in a cascade so that they can reject false samples very fast. Histogram of gradients is another technique which is used to detect objects. It's fast, robust, quite accurate. And what is this? It's a little bit like SIFT, which we talked about. You calculate gradients first. You can use just a one-dimensional vector for X, a one-dimensional for Y, pass it over the image. And then you gather those gradients together in histograms within cells, so groups of pixels. And then you normalize the histograms within groups of cells. And then you just concatenate this and give it to a classifier. An example of Viola-Jones, one of my students in the past used Viola-Jones to try to detect people who could help you in an outdoors health emergency. If you need help, you can try to find close by adults. There's a lot of cool libraries that are out there for object detection, for example, Darknet YOLO. If you want to find facial landmarks, like where somebody's eyes are, their nose are, for example, if you're looking for drowsy drivers, you can use DLive. And I've used these before for trying to detect if somebody drank some water or some liquid. And I was using a thermal camera plus RGB thermal to determine if somebody touched something or if their lips were cold from drinking. Some recent advances in computer vision, there's an increasing convergence of different fields like natural language processing and vision. Transformers are a big topic, which are being used for object detection, image completion, segmentation now. The few shots learners are really interesting, like GPT-3 from OpenAI, which was released this summer. So you don't need lots and lots of data. Also, we're seeing more generation of content by different artificial intelligences like deepfakes. This is a very bad example here on the right, but I'm making this image of my daughter move using a movie of Leonardo DiCaprio. Other nice things to know, OpenCV has some support for machine learning. Latest version was 4.4.0 in the summer this year. There's many, many more fascinating tools and algorithms that you can check out, like optical flow, motion history, images. A little question. How could a robot tell the difference to a robot in front of it using computer vision, do you think? You can stop your video here if you want to think about it, otherwise we go on. Well, there's really many, many different ways that a robot could do this. You can find markers. For example, at Halmstad University, one of our professors has created some spiral markers that are quite nice. You can use readily available markers like Haruko. You can use shape, Huff transform, template images, features like Sifter Orb, Viola Jones, color picking, motion. Well, that's it for today. Thank you very much for listening. Hej då!